In this video lecture, we have to study the concept of multipole expansion. Multipole expansion is a mathematical tool for finding the electric potential at a distant point due to a localized charge distribution. Here, localized charge distribution means that the charges are confined to a region whose size is much smaller than the distance to the point at which the potential is studied. See this schematic representation. Inside the localized charge distribution, we have considered a charge element which is at a distance r dash from the origin. At the point P, we are going to calculate the value of potential. The point P is at a distance r from the origin. R and r dash are vectors. Here, the value of r is far greater than r dash. If you assume the size of this charge element as 5 centimeter, we are recording the potential at a distance of 50 meter from the charge element. In this way, we should realize this fact: r is far greater than r dash. In general, potential is given by the formula V equal to Q divided by 4 pi epsilon naught r. This is the general formula for electric potential. But for this schematic representation, we have to write the potential V, which is equal to 1 divided by 4 pi epsilon naught integral rho of r dash d tau dash divided by modulus of r minus r dash. Here Q is replaced by integral rho of r dash d tau dash. As pointed out earlier, this localized charge distribution consists of many charge elements. Volume of each charge element is d tau dash. Therefore, the density of a charge element is rho of r dash equal to dq divided by d tau dash. Then dq, which is equal to rho of r dash into d tau dash, then q equal to integral of rho of r dash d tau dash. In this way, we have presented this formula for potential. Now, we have to find out the value of 1 divided by r minus r dash. For that, we have to consider the cosine rule. These two sides are known to you. The unknown third side is given by the cosine rule: r minus r dash whole square is equal to r square plus r dash square minus 2r r dash cos theta. This is our r minus r dash whole square value according to the cosine rule. Using this cosine rule, we have to find out the value of 1 divided by r minus r dash. One divided by r minus r dash equal to 1 divided by r square plus r dash square minus 2r r dash cos theta entire power half, which is equal to 1 divided by r into 1 plus r dash square by r square minus 2 r dash by r cos theta power half. Here, put x equal to cos theta and r dash by r is equal to t. Now the above equation becomes 1 divided by r minus r dash equal to 1 divided by r into 1 minus 2xt plus t square power half. Now you have to find out the value of 1 divided by 1 minus 2xt plus t square power half in terms of Legendre's generating function. The value of 1 divided by 1 minus 2xt plus t square power half, which is equal to summation over n equal to 0 to infinity Pn of x into t power n according to Legendre's generating function. If you put n is equal to 0, we can get p0 of x. If you put n equal to 1, we can get p1 of x into t. Then n equal to 2 provides p2 of x, t square, and the series is continued. Put a plus and dot. This is the value of 1 divided by 1 minus 2xt plus t square power half. Now, this equation is modified as 1 divided by r into p0 of x plus p1 of x into t plus p2 of x into t square. Now we have to find out p0 of x, p1 of x and p2 of x using our Roderick formula 1 divided by 2 power n factorial d power n divided by dx power n into x square minus 1 power n. This is the Roderick formula. Using this formula, we have to evaluate the values of p0 of x, p1 of x and p2 of x. If n equal to 0, then p0 of x equal to 1. If you put n equal to 0, anything but 0, 1. If n equal to 1, then p1 of x, which is equal to 1 by 2. 2 power 1 to 1 factorial 1, so 1 by 2. Then d by dx of x square minus 1. Here n equal to 1. This is equal to 1 by 2 into 2x. d by dx of x square minus 1 is 2x. This is equal to x. But you have substituted x equal to cos theta, so p1 of x equal to cos theta. If n is equal to 2, then p2 of x, which is equal to 2 square 4, 2 factorial 2, 4 into 2, 8. 1 by 8 d square by dx square of x square minus 1 whole square, which is equal to 1 by 8 into d by dx of x square minus 1 whole square, which is equal to 1 by 8 into d by dx of 2 into x square minus 1 into 2x, which is equal to 1 by 8 into d by dx of 4x into x square minus 1. If you differentiate this, we can get 1 by 8 d by dx of 4x, is 4 into x square minus 1 plus 4x into 2x. Just we have to use UV formula. This is U, this is V. This is equal to 1 by 8, 4x square minus 4 plus 8x square, which is equal to 1 by 8 into 12x square minus 4. If you simplify this, you can get 1 by 2 into 3x square minus 1. Then P2 of x equal to 1 by 2 into 3 cos square theta minus 1. Because x is cos theta, so x square is cos square theta. So these are all the values of P0 of x, P1 of x and P2 of x. Now we have to substitute all these in the above expression. Now the value of 1 divided by r minus r dash is equal to 1 by r 1 plus the value of t is r dash by r. P1 of x is cos theta. The value of P2 of x is 1 by 2 3 cos square theta minus 1, then r dash by r whole square. T square is this much. The series is continued. If you simplify this, we can get 1 by r square. So here 1 by r. First term is 1 by r plus 1 by r square r dash cos theta. This is the second term. And the term third is 1 divided by 2r cube r dash square 3 cos square theta minus 1. 1 by r into r, 1 by r square, then r dash cos theta, 1 divided by r into 1 by 2, here r square, so 1 by 2 r cube, r dash square 3 cos square theta minus 1. Now the potential V equal to 1 by 4 pi epsilon naught integral rho of r dash d tau dash divided by modulus of r minus r dash, which is equal to integral rho of r dash d tau dash divided by 4 pi epsilon naught. Then the value of 1 divided by r minus r dash is equal to 1 by r plus 1 divided by r square r dash cos theta plus 1 divided by 2r cube r dash square 3 cos square theta minus 1. Now you have to simplify this. V equal to 1 divided by 4 pi epsilon naught r integral of rho of r dash d tau dash. This is the first term. And the second term is 1 divided by 4 pi epsilon naught r square integral r dash cos theta rho of r dash d tau dash. And the third term is 1 divided by 4 pi epsilon naught r cube 1 by 2 integral r dash square 3 cos square theta minus 1 rho of r dash d tau dash, and the series is continued. See here, we have expressed the potential in terms of different terms. The potential is expressed as series of monopole, dipole, quadrupole and other higher order terms. So that we are calling this one as a multipole. Now we have to provide the physical significance of all these terms. Among the aforementioned terms, only the non-zero terms are contributing to electric potential. Now consider the first term, which is called monopole term. Monopole term is given by the letter capital Q. If the total charge is 0, the monopole term becomes the leading contributor to the electric potential monopole term is non-zero. If the total charge is non-zero, the monopole term becomes the leading contributor to the electric potential at a distant point. This is a condition for the presence of monopole term. If the total charge in a localized distribution is non-zero, the monopole term becomes the leading contributor to the electric potential at a distant point. This is Q equal to summation over Qi not equal to 0. Suppose the localized charge distribution contains so many charges, plus Q, plus Q, plus Q, plus Q, then minus Q, minus Q, minus Q, like that. If you take up the sum of all these charges, 1, 2, 3, 4 in positive, 3 in negative, the resultant charge is plus Q, which is non-zero. At that moment, the multipole term dominates to electric potential at a distant point. If you sum up the charges, if the sum value not equal to 0, then monopole term dominates. Suppose the sum value is 0, the monopole term is vanished. If the total charge is non-zero, the monopole term becomes the leading contributor to the electric potential at a distant point. So Q, which is equal to summation over Qi, not equal to 0. Here the monopole term varies as r power minus 1. Next term is dipole term. See this dipole term, it's a vector which is equal to 1 divided by 4 pi epsilon naught r square integral r dash cos theta, then rho of r dash d tau dash. In the above expression, if you put r dash cos theta, which is equal to vector r dot r cap. We know that a dot b equal to ab cos theta, so we may write modulus of vector r, modulus of r cap into cos theta. But modulus of r cap is unity, 1. So r cos theta, this is r dash dot r cap. R dash cos theta is R dash dot R cap. Modulus of R dash into modulus of R cap cos theta. A dot B equal to AB cos theta. So general formula. But modulus of R cap is unity. So this is R dash cos theta. Therefore we can write R dash cos theta equal to R dash vector dot R cap. So the above expression is this dipole term, which is equal to 1 divided by 4 pi epsilon naught R square integral of R dash dot R cap rho of R dash d tau dash. But our dipole moment, which is equal to rho of R dash d tau dash into R dash. This is our dipole moment. So dipole term, which is equal to 1 divided by 4 pi epsilon naught R square vector P dot R cap. This is our dipole term. Now we have to provide the explanation for this. If the total charge is 0, but the net dipole moment is non-zero, the dipole term becomes the leading contribution to the electric potential, at a distant point. See here, among the different terms, only the non-vanishing terms are contributing to electric potential. In order to include the dipole term in our potential calculation, this condition should be satisfied. If the total charge is 0, but the net dipole moment is non-zero, dipole moment is a vector, net dipole moment is non-zero, the dipole term becomes the leading contribution to the electric potential at a distant point. So second term is dominating. This is dipole term. Here the potential varies as r power minus 2. To understand more about this, consider a simple example. Two charges, minus q and plus q, are symmetrically placed about the origin. This is at a distance of minus d by 2, plus q is at a distance of plus d by 2. You know the value of dipole moment. Here P equal to minus q into d by 2 plus q into plus d by 2, which is equal to minus q into minus d by 2 plus q into plus d by 2, which is equal to q d by 2 plus q by 2, which is equal to q into d. Now we have proved that the net dipole moment is non-zero. In this case, if you take the sum of these two charges, we can get 0. But here the charges are, even though symmetrically placed, the net dipole moment vector is non-zero. Under this condition, the second term, which is our dipole term, contributes to the electric potential at a distant point. So in this way, we should realize the dipole term, and we have to go for the third case, quadrupole term. Quadrupole term is a tensor. Quadrupole term, which is given by the formula q suffix ij, which is a tensor quantity. Suppose qij not equal to 0, the term is dominating to the electric potential. For that we have to write the condition. If the total charge in a localized distribution is 0, if the total charge is 0 and the charges are distributed about the, and the charges are symmetrically placed about the origin, symmetrically placed about the origin, such that the net dipole moment vector is 0, the quadrupole moment becomes, quadrupole term becomes the dominating factor to the electric potential at a distant point provided that the quadrupole moment is non-zero. Quadrupole moment is non-zero. See this, if the total charge is 0 and the charges are symmetrically placed about the origin such that the net dipole moment vector is 0, the quadrupole term becomes the dominating factor to the electric potential at a distant point, provided that the quadrupole moment is non-zero. Now we have to prove this with the help of a simple example. Consider a square with the sides 2a. This is a square. This side is 2a, this is 2a, this is 2a, this is also 2a. Then 4 charges, minus q plus q, minus q plus q, are placed symmetrically about the origin. About the origin, all these charges are positioned at a distance of a. Consider a graph sheet. This is origin, this is x, this is y, this is minus x, this is minus y. So from the origin, this minus q is placed at a distance of minus a comma a. With respect to x, which is minus a. With respect to y, this is plus A. Here both are positive, A comma A. This is A comma minus A. This is minus A comma minus A. This is X, this is Y. XY, XY, XY. See, this is a specification. With the help of this, we have developed this. Now, we have to prove that summation over Qi Ri equal to 0. See this. If the total charge is 0, sum of all these charges minus Q plus Q minus Q plus Q, 0. And the charges are symmetrically placed about the origin. From the origin, all these 4 charges are symmetrically placed. And then we have to prove the net dipole moment vector is 0. Now we have to prove that summation over Qi Ri equal to 0. This is the dipole moment vector. For that, consider the value of Q1 R1. Q1 R1 equal to, put this charge minus Q, then this is minus A into I plus A into J. Then Q2 R2, which is equal to plus Q is A into I plus A into J. Then Q3 R3, which is equal to minus Q into A into I, then minus A into J. Then Q4 R4 plus Q into minus A into I minus A into J. We know that dipole moment is a vector, so that we have expressed X and Y in terms of I and J. Take the sum of all these things, Q1 R1 plus Q2 R2 plus Q3 R3 plus Q4 R4. If you make the sum of X coordinates, minus Q into minus A plus QA plus QA, then minus QA, 0. Then sum of the Y coordinates, minus QA plus QA. Here plus QA minus QA, 0. So summation over Qi Ri is equal to 0. So this condition is also satisfied. Therefore, the quadrupole term becomes the dominating factor for this case, provided the quadrupole moment is non-zero. So in this way, we should realize the term multipole expansion. Here the potential is expressed as a series of monopole, dipole, quadrupole and other higher order terms. Among the aforementioned terms, only the non-vanishing terms are contributing to the electric potential. Thank you.